right, good morning. I'm Stephen Sprouse. I'm an engineer in the systems architecture group at SanDisk, and I work on enterprise drives. And one of the things that has happened in the when I started at SanDisk, I remember the first drive I worked on was a 1 gigabyte USB thumb drive. That was about 20 years ago. And it's just incredible now that when I look at our roadmap, a few years out, we actually have petabyte drives now on our roadmap. And but one of the things that we've seen in the last few years as we've accelerated in these very, very high capacity drives is that the time to do preconditioning of these drives has increased dramatically. Previously when we were doing 1, 2, 4 terabyte drives, the time to do a preconditioning was a matter of less than an hour, maybe an hour or two. And recently, as we've gone to these high capacity QLC drives, the capacities have been doubling every few years, but the write performance, especially when we go from TLC to QLC, has not been keeping pace. So the net effect of that is the time to do the preconditioning is gone from hours to days. Sometimes it can be a week if you look at some of the high capacities that we're looking at, just to do the preconditioning phase of a random write test. This sort of spawned us to look for ways to improve this. So we started first looking at what is the goal of preconditioning, right? So there's two main goals. One is just to make sure that every logical address, every LBA is written at least once so that it contains valid data. And then the other goal is to reach this kind of steady state behavior, which is really a result of redistributing what we call the overprovisioning within the drive in a particular way. So, and what that distribution looks like is sort of shown in this diagram here. The way to interpret this diagram is if you imagine like the full rectangle being the physical capacity of the drive, the physical media. The gray area is sort of the logical capacity of the drive that we export to the user, and the red portion is what we call the overprovisioning. It's the extra media that we use, especially in the random write case, to improve the performance. And so that when the drive hits steady state in a random precondition, this distribution is sort of what emerges, and this is the goal of what we want to have when we have properly preconditioned the drive, something that looks like this. So, and one of the key things to look at is on the left-hand side is that sort of the ratio of the red to the gray on the left-hand side is where the write amp emerges. So this is an example of a drive that has 15% OP. So the red part would be roughly 15% of the total rectangle. And the write amp in this case is about 4. So there's sort of a 3-to-1 ratio between the gray and the red region if you take a vertical slice on the left-hand side. So we were looking for ways that could we accelerate getting into that state faster than is sort of the traditional way of doing preconditioning? And can we do this in a way that we can sort of compare our method with the way that the traditional preconditioning method is done? So if you look at the way that the conventional preconditioning is done, is you first start off with what we have on the left-hand side, where you do one or more sequential writes. And the main purpose of that sequential write is to logically fill the drive, okay? We've been, if you look at the SNIA standard, I believe the SNIA standard says you should do 2 sequential writes, and we're not sure whether that's relevant anymore. At least with our drives, when you do that first sequential write, it served its purpose. But anyway, you would first do this sequential write pass, and that diagram on the left is what the distribution of OP looks like after that first sequential write. So you have a region of gray where the drives are, those regions are 100% valid. They don't contain any over-provisioning. And then you have some regions, blocks that are 100% invalid. And that's why you kind of have this vertical red box on the left. And so after you've done that sequential precondition, then you switch to your random write preconditioning, which in the conventional approach, you start doing a random write, and you see this, this over-provisioning starts to get distributed across the media within the drive, and it progressively shifts within the drive until you get to that steady state on the right. Now the problem is that while you're doing that random writing, there's actually garbage collection starting within the drive, and so the performance of the drive will slow down, and it will also kind of gyrate until you get to that steady state. So the goal of this Sprandom technique is to see if there's a way that we can get to that end state in a single physical drive write. And what I'll show you in the next few slides is the technique that we developed in order to do exactly that. So if we can do that, we can accomplish both goals of every address is written once and only once. And we can do that before garbage collection kicks in, meaning that we can do it very fast because we're not competing with any background operations. So the way we do that, the first approach that we used, we did this using just FIO and its kind of off-the-shelf state. We divided the drive, in this example, into 10 physical regions. So the sum total of the gray areas on the right would represent the physical capacity of the drive. And then along the vertical axis, we have the logical capacity of the drive. And if you see what we're doing here is we are having a little bit of logical overlap from each write region to each write region. And that overlap is designed to create a little bit of invalidation, which creates, that the invalidation is how we create the OP distribution. So by having a little bit of overlap and modulating that overlap as we write through the drive, we can actually create the exact amount of OP distribution that we want within the drive. So this was the first approach we used, and we got very good results with this. Now, so the previous slide sort of outlines a mechanism for creating an OP distribution. So the other thing you need to know is what does that OP distribution need to look like, okay? So this diagram sort of shows how we came up with that distribution. So it's based on a paper that was written, published in 2012 by Peter Desnoyers and some other researchers. And in that paper, the main equation in there that people were interested in was an equation that described the relationship between write amp and over-provisioning. So it gave kind of one of the first equations that described, given an amount of OP in a drive, what would be the write amp? And from that write amp, you could deduce a lot of things like what would be the expected performance. But there was another equation in there, it's equation 5, which is also interesting because it's I times F sub I equals K. Because this equation describes how the OP is distributed through the media within the drive. So we took that equation and I'll walk you through sort of the interpretation of it. But if it basically says that for any amount of, given a certain amount of invalidity, how much of the drive will be in that state. Okay, so what we've done here, if you look on the left-hand side of this diagram, we have these dashed red lines, which have sort of segmented the region above the line into evenly spaced regions. And what we're looking for is each of those represents a particular amount of invalidity. So it's proportional to the I term in the equation. And what this is saying is that given a certain amount of invalidity, how many blocks or how much of the media is going to be in that state. And furthermore, for every amount of invalidity, that if you take the amount of invalidity times the number of blocks in that state, that's going to be a constant. Okay, so that's pretty interesting. So what you can see here is the area underneath the curve for each of these regions is constant. And so you can see that but because the validity of each region is different, you can see that the width of each of these regions is changing slightly. So we have more blocks, or it's wider on the left, and it's more narrow on the right, even though the net area underneath the curve is the same. And if you think about this, from a random right steady state point of view, the interpretation here is that if you're sort of picking addresses from the drive randomly, when you're in steady state, you should have an equal chance of picking an address from each of these regions. So the rate that you're sort of transitioning from one region to the other as you're creating invalidity is equal. So when you get over to the left-hand side of this curve, that's the block that you're going to choose to garbage collect in a greedy algorithm. Okay. So, and we know the amount of validity at that point is basically this 1 minus 1 over the right amp. Okay. So given that we know sort of where this curve intercepts on the left-hand side, because if we know the OP, we can determine the right amp, and if we know the right amp, we can use this formula 1 minus 1 over the right amp to get the validity. Then we can take that region between sort of the GC validity and 1 and divide that up into some number of regions. Okay, so we are able to use this formula to construct this curve, but it's not kind of exactly what we want, in that we want at the end to have physical regions that are all the same. So what we do is we actually go and we resample this curve kind of at fixed steps, so that we still get a particular validity per region, but it's just the regions are all sort of the same width along the x-axis. Okay. So I mentioned before that we wanted, the last thing we need is to sort of understand what is the relationship between overprovisioning and right amp. And that was what was published in Desnoyers' paper. There was another paper actually published, I believe, the same year by another researcher. His name is Krakowski. That also gave a formula that described the relationship between OP and right amp. And so I show this equation here on the right-hand side. The only difference between Desnoyers' equation and Krakowski's equation is just the way that they define OP. So Krakowski defines OP using this formula on the lower right-hand side, where it's basically the difference between the physical capacity and the logical capacity divided by the logical capacity. And Desnoyers' paper just described OP as being the ratio between physical capacity and logical capacity. So we tend to use this definition shown here, and that's why I referenced Krakowski's paper. But anyway, he gives this sort of complex equation that uses something called the Lambert W function. This will give you an exact relationship between write amp and overprovisioning. But there's also an approximation that we use, which is fairly close in the regions that we typically have overprovisioning, and that's write amp is equal to 0.5 over OP plus 0.7. Okay, so if we take the OP in a drive and we extract out the write amp, and then we use that to define this curve, we've sort of outlined all of the steps that we need in order to achieve a fast random precondition, right? So we can derive the curve. We can figure out in each region how much invalidity we need. We can create that invalidity by having very directed overwrites of previous logical addresses. We have this step in there, which is a logical address shuffle, which is that one of the problems with the logical overlapping is it creates a lot of locality within the drive, logical locality. And that's okay for some, for some random write testing or random read testing, but it would not work, for example, if you were doing like a workload transition test, maybe from a random precondition to a sequential precondition. So by kind of shuffling the addresses randomly, we can get to this sort of third diagram with the red and the blue, which kind of eliminates that logical locality problem. And this is actually what we're doing in we've integrated this into the FIO testing tool, and it's been released. I'll show that in a second. But as so you can see that as we modulate the amount of invalidity written in the drive, you can see that the red dots on that diagram are more dense on the left, and they taper off on the right. That's what kind of gives us this ideal distribution of overprovisioning within the physical media. Okay? So one of the things exciting things that happened in the last month was we were working on integrating this capability into FIO. That code was merged into FIO on August 25th, and it was actually released officially in version 3.41 just a couple weeks ago. So it's out there. People can use it, try it out. So the FIO implementation of this really, just needs these additional 3 statements that I show here in the lower right. So you have to enable Sprandom as a portion of the job. You have to tell it the amount of OP. Now the amount of OP that you describe there is the actual physical OP. Like, we talk about sometimes a drive having 7% OP. That's what we would call a kind of a marketing number. But the actual OP within a drive will typically be an extra 6, 8, or more %. So you have to work with your drive vendor, or if you are a drive vendor, you have to look at the actual OP you have in the drive. There are ways to measure this empirically. Using smart counters, you can look at how much data has been written to the media, and how much data has been written by the host, and do a certain amount of. If you get a drive that's already in the steady state with the conventional method, you can actually deduce the actual OP from the write amp. And then there's this sort of number of regions that you want to have the drive being segmented into. This number's, should be, a few hundred. I won't get into too much detail, but it basically can reduce the amount of, the larger you make this, the less memory FIO is going to use internally on the host that's driving the drive. This feature in FIO will work with drives with different IU sizes. So, if you're doing smaller, lower capacity drives, compute drives, say, that have a 4K indirection unit, you can use, it'll work with that. And if you're doing larger drives that have 16K or 32K indirection units, it will also work with that. It basically honors the block size and the block alignment settings that you pass into FIO. And then the last thing is, if you are trying to, let's say, short stroke the drive a little bit, we have some customers that, let's say, want to have an extra 10% of OP in the drive. You can set the size to be, let's say, 90%, in which case you'll have, you actually get a little bit more than 10%. You have to go back and kind of recalculate the OP. It's not just like you take 10% and add it to 0.15. You have to go and do a little bit more math to recalculate OP according to the definition I showed with the Krakowski paper. But that's about it. It's a fairly straightforward interface. So this is an example that I've shown in a few places before. But this was done by the Western Digital OCCL lab earlier this year, where they took a 64 terabyte drive and they ran this Sprandom algorithm. And the problem they were having was they actually want their drives to be in a very steady state, state, and they were taking about 144 hours to get to that state. And when they used the Sprandom preconditioning approach, they were able to reduce that into less than 7 hours. And so this is an example of how they ran the Sprandom precondition, and then when they switched over to the random write workload, it kind of just snapped right to the steady state workload. So it's accelerated their testing of different drives tremendously. Okay. So, my real goal here is we think that this method is a viable way to accelerate testing of these high capacity drives. It is, it's been working in our lab. We've replicated the results with at least 2 or 3 other independent partners. So we're looking to foster adoption of this as an industry-wide standard. So I'm hoping that people in this room or people that watch this talk will try downloading FIO, give it a try. Look for ways that you can apply it in not just your development, but also in production and deployment. And let me know if you find anything that suggest improvements. I have a link here to the FIO code, and as I said before, it's been released in version 3.41. There are discussion sections on the GitHub FIO site where you can ask questions and see some of the tests and questions that were asked before. And I guess one other thing was that this technique, I believe, is not just applicable at the SSD level, that there could be, it could be applicable to any type of system where you have garbage collection going on. So even at a data center level or an application level where you have large structures where you're doing smaller invalidation and then having to do garbage collection at the application or data center level, you could use this technique to get your sort of entire system into a predefined state in a faster than the conventional method of preconditioning. So that's it. So any questions? Okay.